So you're not going to curve.
Hello and welcome back to Calculus 2, section 8.3 post-exam. We just heard about no curve. Yes, no curve. There's no point to a curve. You either know stuff or you don't know stuff. Trigonometric integrals. Yes, we are going to go back and review some of the trig identities that you absolutely must know, or go home, right? And we are going to take a look at the basic integrals first, and then some of the spicier situations that you are going to run into. Now, this section is going to be the prerequisite and a core calculation for the next section, which is trig sub. So pay attention on a double, right? The first we have are the formulas that you absolutely must know or you are doomed. Tangent x is sine x over cosine x. Cotangent x is cosine x over sine x. These are the two introductory formulas. And then we have the Pythagorean identity, sine squared x plus cosine squared x equals 1. If you divide this equation everywhere by cosine, you will get tangent squared x plus 1 equal secant squared x. And if you divide the original formula by sine, you will get 1 plus cotangent squared x is equal to cosecant squared x. I'm going to put these in the blue box, to kind of group them. And then we have the two power-reducing formulas, which you absolutely must know. Sine squared x is 1 minus cosine 2x over 2. And cosine squared x is 1 plus cosine 2x over 2. And box those as well as a unit. So these formulas you need to know even if someone shakes you out of bed at 4:15 in the morning. You should be able to recite all of these half-conscious and then go back to your unconscious state. So these are the formulas, and now we have the first pair. By the way, the trig pairing goes sine, cosine, secant, tangent, and cotangent, cosecant. You can see that pairing in the blue box, right? The way they are paired also through the derivatives and integrals. So we are first going to talk about SineCosine pair. And here you will recall your derivative and integral formulas that you learned all the way back in Calc 1. So you are going to remember that the derivative of sine x is cosine x, which immediately means that your integral of cosine x dx is sine x plus c. And finally, the derivative of cosine x is negative sine x, which gives you that the integral of sine x dx is equal to negative cosine x plus c. So these are your basic Calc 1 formulas, and we just get to use them now, right? Or get to see the introductory basic example that you should know by now from U sub era of, let's say, sine to the 9x cosine x dx, right? So this would be your standard Calculus 1 question that still fits here because it's trigonometric integration, and you might run into one of these or right in the next section as well. So worth reviewing. When we see multiple functions, we immediately look for function derivative pair to see if we can use the basic U sub rather than any other witchcraft that comes up in this chapter. So we see that the derivative of sine is cosine. So the u sub over here is the perfect match. I usually like to say here's the peanut, right? And you can see the peanut right there is the du. And then you have sine to be u, so u to the 9 du. Oh, I put dx. No, du. There we go. So now this is going to be u to the 10 over 10 plus c, and we bring sine. So 1 over 10 sine to the 10 x plus c would be our answer. So that is the standard question from Calc 1 as a warm-up using basic U sub. Now for Calc 2, what we do is we mess with these exponents. So for a Calc 2 question, I still have sine to the 9x, but now I have cosine cubed x dx. So this is your Calc 2 question in comparison to your Calc 1 question up there. So now the cosine has the cube on it, and you have to deal with that as well. And this is where the Pythagorean theorems and Pythagorean identities and all the other stuff, right, comes in. You know that if you are to use the u substitution, just like in a previous problem, you would have to have a single cosine, not 3 of them. So what we are going to do is we are going to peel off one cosine and keep it off in a what I call a bank, and that will leave you with a cosine squared. Now that cosine squared will be turned into sines using the identity, and then you will just solve the problem. So what I do first is I am going to peel off one cosine, and I'm just going to put that here in a bank, right? Because that's for my du. So I put that in a bank, and now the cosine squared over here is going to transfer into 1 minus sine squared x. Because that's our Pythagorean identity, right? Sine squared plus cosine squared is equal to 1. Therefore, cosine squared will be 1 minus sine squared. So now I get to multiply these sine, right, to the 9. So I have sine to the 9x minus sine to 11x, all of that in parentheses, and I have my cosine x dx in the bank over here. So I can just, right, keep that in a bank right there. So now you see that you have sines and you have a cosine in the bank. That means that you can do the same u substitution as before. U equal sine x, du equal cosine x dx, and that gives you the integral of u to the 9 minus u to 11 du, and integrals, right, u to the 10 over 10 minus u to the 12 over 12 plus c. And then we bring back our original variable x, which means 1 over 10 sine to the 10x minus 1 over 12 sine to the 12x plus c. You could simplify this a little bit, right? Pull out 1/2 sine to the 10 and so on, but what happened? Oh, this term over here is obtained when you multiply into the sine, because it gets distributed over the both. So now what you see here, try to fit everything on the screen, would be what we would call the simplest Calc2 version of this, where you have to peel off one of the powers and then transfer. Now, can you peel one of the cosines off? Yeah, you can peel one of the cosines off, but then you would have to deal with sine to the 8th. And sine to the 8th will be sine to the sine squared times sine squared times sine squared times sine squared. And then you have to write each one of those as 1 minus cos. So it just gives a lot of mess. You always want to peel off the one that has less exponent. All right, so now, even if you have one exponent to be even, we can still deal with these fast. So let's say you have cosine to the 6x sine cube x dx. You can still deal with this, right? As long as you have one odd power. The next example will have 2 even powers, and that's going to be the pure evil, right? This one is, so as long as you have one odd exponent, the problem should be straightforward because you will be peeling off, right? Everything good over there? All right. So we are going to peel off one sine x and then have that sine x dx in a bank, which means that I have to use u to be cosine, right? Because if u is cosine, then the du would be sine. And this is also immediately you see that this sine now needs to be transferred into a cosine. So how about you finish this problem off, right, knowing that this is 1 minus cosine squared x. So the same steps as before, distribute and, right, get my emergency puzzle. Okay, so absolutely same steps as before. We multiply, so we get cosine to the 6x minus cosine to the 8x, and we have sine x dx in the bank. We are going to use the u sub, so u equals cosine x, du equals negative sine x dx, so you'll have to mess with the negative signs. So to get the negative signs, you just change, you need a negative sign, right? So if you put a negative there, you have to put the negative in front, which will actually just change these guys. So what we have now is u to the 8 minus u to the 6, just change their spots, right? So you list the positive one first, and that is going to be now u to the 9 over 9 minus u to the 7 over 7 plus c. Bring the cosines in, so 1 over 9 cosine to the 9x minus 1 over 7 cosine 7x plus c. So this is what the cheap sine-cosine combo is. If you have at least one odd, or they're both odd, right, then you can always do the, you peel off one, put it in a bank from the odd one, transfer the rest using Pythagorean identity to the other trig function and deal with it. Now, the evil situation is when you get two even ones, right? So if you have integral of sine squared x cosine squared x dx, holy nightmare, right? Because in this situation, if you peel off either sine or a cosine, the remaining amount will be odd, and the Pythagorean identity doesn't work anymore. So we have to have completely different method on solving when you have two even. Now that can be 2 with a 4, 4 with a 4, 2 with a 6, 4 with a 6, right? And obviously it gets much more complicated and worse as your exponents go higher. This is the cheapest problem that you can possibly have. The next one is either of these to have a 4, and the other one keeps a 2, which you are highly encouraged to do on your own when you go home. So change any of the squares to a 4 and practice. You should have a homework, obviously, on it. So now, there are a few different ways we can attack this. I'm going to go with the standard way and then the boss way after that. The standard way is you just deal with these two problems using the
integration backward.
Power reduction. So we're going to power reduce both of these. We have 1 minus cosine 2x over 2 and 1 plus cosine 2x over 2. And now we are going to multiply those. It kicks 1/4 in front of the integral. And then this is now difference of squares, which is 1 minus cosine squared 2x dx. And we have to use power reducing one more time to kill that square. So it's 1/4 integral of 1 minus, and now I have 1 plus cosine 4x over 2 dx. So we used power reducing formula here couple of times. I used it 3 times so far. So when you power reduce initially, then you have to multiply them, and when you multiply them, you get another square, and you kill it now over there. So your single x got doubled into 2x, and then the 2x input got doubled into 4x. Usually that's where your grade dies, because you forget to double the power, the angle. And now I can just work out the algebra first. So integral of 1 minus 1/2 minus 1/2 cosine 4x dx, which is 1/4 integral of 1/2 minus 1/2 cosine 4x in parentheses dx, and you can kick out the half to give you 1/8 integral of 1 minus cosine 4x dx. And now you have basic integrals to deal with. So we had to convert the entire problem into this. So we had split the fraction over the plus there, but the minus will distribute to both terms. So we got -1 and minus cosine, and then a half for a 1 and a half for a cosine, and then 1 minus a half is a half, the other half stays as a half, and then you pull the half outside, and this is what we get. So now we can integrate using basic integration. This is 1/8 x minus the integral of cosine is a positive sign, 4x. Don't forget to put over 4, because it is by that 4. When you have the 4 in the angle, right, it goes out as a division. And that's it. There was no U sub in this question. It was just a ton of algebra, right, to solve this. Now, one of my students said, you could have, and gave me this other option, which is really cool. So I want to also show that off. So the boss way to solve the problem is, this student realized that you can write this as sine x times cosine x times sine x times cosine x dx.
Oh.
Isn't it sine squared sine times sine, and a cosine squared cosine times cosine?
Yeah.
Now, why did he suggested this? He suggested this because there is a formula which says that sine 2x is 2 sine x cosine x, right? So you have two of these sets. So now you have over here, you have sine 2x over 2 and another sine 2x over 2. And you kick out a quarter and you get sine squared 2x dx, and you have to use power reducing only once. And you use power reducing only once, this becomes 1/8 integral of 1 minus cosine 4x dx, which is exactly where we were here. It's a really cool transformation, and it does help a lot in certain cases. So now this problem is done, because the next step, right, is to just integrate this 1/8 x minus sine 4x over 4 plus c, and be done. So that was another way. So now let's sum up SineCosine pair. So if you have integral of, well, let's put it this way, integral of sine to the mx cosine to the n x dx, and we'll have two possible cases. Case number one, if any or both are odd, we peel one sine or cosine x off, and use it for du. Now, this is, a sentence really bare minimum of information given because you are supposed to learn how this thing works, right? Number 2, both even. That's the evil part. When both even, power reduce. So power reduce until you will have to power reduce and multiply and then power reduce again and multiply and power reduce again and multiply. So if you should really try, a problem that has a 4 and a 2 in it, and it should take you some time because you see that I had to power reduce 3 times for 2 and 2, and I promised you that that's the cheapest possible case you can have, right? So with higher exponents, you will have to power reduce more. And then, there was that neat trick of sine squared, sine 2x. But, can't bank on that one every time. So that's the sine-cosine pair. And you only have these 2 cases when you look at if at least one is odd or both are odd, those are easy. And then when both are even, they're not hard, they're just annoying, right? Because you have to do a lot of power reducing. Obviously, if you don't know power reducing, you can't do anything. You gotta learn power reducing, right? The next one is tangent secant pair. And that one will also have, tangent secant pair will also have their own formulas from Calc 1, and then we'll take a look. Now, this one is far trickier than sine and cosine, so let's focus here. So we have the derivative of tangent x is secant squared x, which gives us the integral of secant squared x dx is tangent x plus c. And the second formula is the derivative of secant x, which is secant x tangent x, which gives us the integral of secant x tangent x dx is secant x plus c. So this is your Calc 1 knowledge. And in addition to this, you need to know the Pythagorean identity 1 plus tangent squared is secant squared. If you want to add that to the list right now, you can. 1 plus tangent squared x is equal to secant squared x. That's the one that will be used to put these things together. All right, so how would I work on these examples? Let's say we start with the integral of tangent x secant squared x dx. Guys, this is your Calculus 1 question. Right? This is a Calc 1 question. You are supposed to know that the derivative of tangent is secant squared, which immediately means that you have the function derivative pair present. You can do your u sub. So immediately u equal tangent x, du equal secant squared x dx, and we have integral of u du, which is u squared over 2 plus c, which is 1/2 tangent squared x plus c, and you move on with your life. Also, Calc 1 question is integral of square root of tangent x secant squared x dx. So this question is the same as the previous one. I don't care what kind of exponent you have on a tangent. You have a tangent, you have a secant squared, it's a u sub, right? So this is the skill that you have to learn now and recognize. Regardless of what the exponent of tangent is, if there is a secant squared, you're good to go, right? Secant squared is going to be in the bank for du. So same u sub as before. This time you're integrating root of u rather than u. So we have u equals tangent x, du equals secant squared x dx, and that just gives us integral of root u du, which leads into u to the 3/2 divided by 3/2 plus c, which is 2/3 tangent to the 3/2 x plus c, and we are done. So both of these problems, guys, are Calculus 1, Chapter 5.5, Section 5.5 problems. So that's right. Let's do Calc 2. Calc 2 is when you have the integral of square root of tangent x secant to the 4x dx. So now you are wandering into the realm of Calc 2. Now, yeah, it's only an algebraic manipulation, right? But still, this would be the Calc 2 integral, where substitution is not obvious, right? And you have to do extra work to make it fit. Well, now for tangent secant pair, if you are using tangent as a u sub, and you should, because the tangent is the one that is stuck under the root, so tangent is the one stuck under the root, which tells us that tangent should be u. Derivative of tangent is secant squared, but I have secant to the 4th. So we are immediately going to break it apart, right? Into secant squared x and another secant squared x dx, where the second one goes in a bank for du. And this is where you go, well, these secants need to be moved. And luckily we have that Pythagorean identity that will move these secants into 1 plus tangent squared x. And now we can distribute and multiply, right, to get this. So the first one is tangent to the 1/2 x, and the second one is plus tangent 1/2 plus a square is 5/2 x, and then dx, right? So this is what we have. Where's my secant square? Holy nightmare. Secant squared x dx. There we go, much better. So when you multiply tangent to 1/2 exponent, because you have a root, 1/2 times the 1 is just 1/2. And then over here you have a square, tangent square. Tangent square, you add exponents, so you have a 2 plus a half. 2 plus a half is 5/2. So now you get to do the u sub, because now you have tangents for u, and du is secant squared x dx, which is exactly what you have in a bank for it. So this becomes u to the 1/2 plus u to the 5/2 du, basic integrals, right? U to the 3/2 over 3/2 plus u to the 7/2 over 7/2 plus c, and that will be 2/3 tangent 3/2 x plus 2/7 tangent 7/2 x plus c. And now you get to see the full Calculus 2 question, right? Because of the secant to the 4th. So when the substitution is obvious, it's just Calc 1, right? derivative of tangent secant squared, move along with y, right? Any questions? Or just speechless? Speechless, right? At this point. Yes.
If you have like cosine 4x times cosine 2x, can you combine those?
There are formulas that can combine those, yes.
Okay.
But those are special type of formulas that you use. So we don't use them here. They can be forced, but
You can't just make it like cosine 8x squared.
no.
Okay.
There are special formulas. They're called product to sum and sum to product, and they work with adding angles and all of these kind of things. So it's far more involved than they're usually given during the trig course to students, which is why no one knows them, and they do pop up in DFQ actually. So when they pop up in differential equations, it's been 2 years since, everyone goes, oh, and then the panic hits because they were given to students in pre-calc 2, then 2 years later DFQ hits and they're needed.
You're talking about like the half angle, double angle, stuff like that?
No, I'm talking about product to sum and sum to product. So here we go. I'm actually going to real quick find the formulas on the sum to here. So this is what these formulas look like, and so this is the top there. Over there is a sum to product, and you can see that you have cosine plus cosine and then different angles, and here is your product to sum, which is sine and a cosine and sine and sine and sine and cosine. Right? So there are 8 formulas there, and those are always given to students. So once you reach DFQ, you need the blue box, and everyone's like, oh. Let's go and take a look at more of these fun problems. So another tangent secant thing. So what are we going to do now if we have a secant to the 6x tangent x dx, right? So you have this situation. Well, there is a way, annoying as hell, but there is a way to do this problem by peeling off 2 secants. Then you're left with 4 secants. Change those into square times square. Use the identity, right? Go through all of that mess eventually to get an answer. Or, you know that derivative of secant x is secant x tangent x dx. And that is where you realize that you can just peel 1 secant off and then have it u to the 5. Again, a lot of trial and error with these problems until you get used to the way they're done. So secant tangent goes in a bank for du, and now you have your integral of u to the 5 du, which is u to the 6 over 6, plus c, which is 1 over 6, secant 6x plus c. And as I said, this problem can be done the other way, but the other way will take much longer. Now I want you to use this example and solve the integral of secant to the 8th x tangent cube x dx. So it's going to be the same idea, just one step extra. So, you know, bake on it a little bit. Any ideas? Yes?
Separated one secant x, one secant x and one tan x, and then I'll reduce tan x squared into, change not powers, but change tan x squared into the secant squared x minus 1.
Excellent. So we're going to peel off a secant, and we are going to peel off a tangent and put that in a bank. And then we're going to transform this tangent into secant squared x minus 1. So the integral transforms into secant to the 9x minus secant to the 7x times secant x tangent x dx, and this is where u sub kicks in. And get u to the 9 minus u to the 7 du, which is 1 over 10 secant to the 10x minus 1 over 8 secant to the 8x plus c. Looks very simple when you see the solution, but then when you're trying, right, gets to be a living hell. So there are these problems where your knowledge of the derivative of secant and a tangent saves your bacon, right? Saves you. Because you are going to put in a bank either a secant squared, or you're going to put in a bank secant tangent, and different problems will have different, right, situations, right? What you can do. And then there's a group of those problems where none of that stuff works. There. Boom. Pam pam. So we are working on a secant tangent pair, and just to start off the problem, no tangents, right? That's the first issue you immediately see. But then you say, hold on, if I peel off two secants, I can transfer them to tangents. Go ahead, see what happens. It's not going to work out, but just, it's worth trying. So transfer peel off secant squared, transfer to tangent, and you will see that your u substitution is not possible because the stuff is backwards. But it's worthwhile trying. You also need to know the situation when you're supposed to walk away, right? Well, that's one of those, right?
I am not good at that in all aspects of my life.
I'm about to say the artwork is only finished is only done. Right? So the art of walking away.
So far you have seen that doesn't work. Now, the splitting is the right step, but what comes later is the trick. So there is really nothing else that you can do other than break off the square, right, and the single. And now we get to use integration by parts, because we can integrate secant squared and we can differentiate anything. So integration by parts kicks in as u equals secant x dv equals secant squared x dx. And we established earlier that integral of secant squared is a basic tangent. So du is going to be secant x tangent x when we differentiate dx, and v is just tangent x. We put our arrow, which we learned about last time, to help us with this calculation, and we write the integral of secant x tangent x, that's uv, minus the integral of tangent squared x secant x dx. So derivative of secant is secant tangent, integral of secant squared is tangent, and we have now this problem. So what do we see here? Can we solve this? Well, no, right? Because the square is on a wrong term, right? If you want to put u to be tangent, you need secant squared. You don't have that. And if you put tangent secant for du in a bank, then you need another secant, but you will have only one tangent. You can't transform. So you're stuck. Well, just do integration by parts again. Or, even better, here's the trick. Transfer this tangent squared into secant squared minus 1. And now, say secant x tangent x minus the integral of secant cubed x minus secant x dx. Now you know you can separate this into two integrals, right? Which is secant x tangent x minus the integral of secant cubed x dx plus integral of secant x dx. So what did we get? What did we get? Apart from headache. Headaches are okay. It's just Calc 2. We know that. There's nothing we can do about that. Cubed. So does anyone remember the trick?
You change your
No. Everything is good so far. We got another secant cube, guys. Recursion. You move the secant cube to the left of the equation, right? Because you have the secant cubed on top, equals to that expression on the bottom. Move the secant cube to the other side, make 2 of them, and then divide both sides by 2. So now what we have is that the integral of secant cubed x dx is equal to the secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. We take this one and we move it their way to create 2 integrals of secant cubed x dx. That gives us secant x tangent x plus the integral of secant x dx. So now the integral of secant cubed x dx is 1/2 of secant x tangent x plus the integral of secant x dx. And we have the answer for secant cubed. But then some of you might go and ask, hold on. There's the integral of secant right there. Right? Oh, well, that's the nightmare on its own. So let's go do that. This method that we just used for secant cubed, you guys have seen last class when we learned integration by parts. If I go back to your previous lecture, 8.2, we are going to see the trig problem, which I labeled the evil one before, and we have seen that the same trick was used to make 2 of the integrals, but your answer at least did not have integrals on the right-hand side. So the method should not be new, the one that we just covered. The problem with this, a huge problem with this, is that your answer now ended up having another integral that is not a basic integral. And for this one, right, you really need to know a trick. This over here is a procedure. Was demonstrated before. You might be able to do it, you might not be able to do it. But what follows for the integral of secant is the pure evil. And that's the new title. The pure evil. The integral of secant x dx. Because you would get 1 over cosine, you are missing sine for u sub. Right, so if you're using cosine, 1 over cosine, you don't have a sine for u sub, so you can't do it. There are no exponents to split anything and so on. And the reason why this one is pure evil is, if you have memorized the exact way to do it, you can do it. You have to memorize a specific function that you have to multiply into this expression to, right? So that's why people don't bother. They just memorize the answer, right? And be done. So here is that function. So your secant x needs to be multiplied by secant x plus tangent x over secant x plus tangent x, and then you still have your old dx. So this is the function that you have to multiply, and now I go and write secant squared x plus secant x tangent x divided by, I'm just going to change these order into tangent x plus secant x, still the same thing, dx. So if you take a look at the orange stuff is 1. But it's the particular function that makes it into a transformation that you have down there And now that you have this transformation, dare I say, U substitution is obvious. Because the derivative of tangent is the secant squared that you have up there, and the derivative of secant is secant tangent. So, if I make U tangent x plus secant x, then the du is derivative of tangent is secant squared x plus derivative of secant is secant x tangent x everything dx. And that's exactly what we have on top. So this becomes du over u for the ln of absolute u plus c, which is the ln of secant x plus tangent x plus c. And this gives you a formula. Integral of secant x dx is equal to ln absolute secant x plus tangent x plus c. As a student, I just memorized that one because I wasn't gonna go and memorize the function that transforms this so I can use u sub and solve it. As a student, I just went and said, oh, the only basic trig functions that can be straight up integrated are sine and cosine, right? Those are the only ones. Tangent, you have to figure out the formula using sine over cosine and u sub. And secant, so all the other fours are not basic integrals. But they still follow their trig pairing. So if you take a look over here, the integral of secant is still having a secant and tangent in the answer. So at least, you know, there is that much that you don't have to involve another trig function. You know, if it's a secant, tangent is with it, and that's it. All of the formulas have to have only secants and tangents. So now that we did this thing in blue, I can insert this answer into the black problem, right? And finally get the answer that the integral of secant cubed x dx is equal to 1/2 open parenthesis secant x tangent x. Was that a minus or a plus there? Plus ln of secant x plus tangent x, and then everything plus c. You got a month to rehearse this by for the Thanksgiving dinner. No, the whole month of just pounding on this one integral. So someone says, what do you know? Or, hi, how are you? What's new?
It's funny you should say that, because my grandparents, whenever I see them, always ask me just like that, so what's new? No matter what I say, no matter what, it's always going to be that. And this time, I think I'm going to...
You're going to whip this one out. Yeah, this is the
Grandpa,
one. You just put this one on the table. Here. Look at this. We use the recursion for some. First we go with integration by parts. We use the recursion eventually to bring it back. Now you have the issue of integral of secant x, which has this function following. Right? And everyone is a winner. You're practicing math, right? They know what's new because they asked, so they were interested. So everyone is a winner.
Okay.
In this situation. Guess what I'm going to use today at the party? There's going to be about 40 people there. Yeah. Hey, I want to see what's new. I mean, this is not new to me, but it's definitely going to be new to them. So.
So how do you know when you have to do it with the integration by parts, when you have to do it by...
You're going to hate my answer.
Practice a lot.
Experience. This is my natural habitat. You're observing me in my natural habitat, right? So it's tons of problems, tons of practice, and luckily exam is not next week. So pounding on the problems. What if I put secant to the fourth? Yeah. Integral secant to the fourth. This problem immediately becomes a joke, right? Because secant to the fourth is secant squared times secant squared. One of the secants goes into tangents, and done, right? Is that u sub immediately done, right? So the difference between secant to the third and secant to the fourth is huge, right? And this is why I say it's experience, right? You're going to go and memorize every single example? Hell no, right? But the good thing is that the bag of tricks is finite. And the bag of tricks, here it is. The bag of tricks is, for your u sub, your bank is either secant squared or secant tangent, right? If that doesn't fit, that killed u sub, right? If that doesn't fit, it killed your u sub. The only other option you have is integration by parts. And it's the end of the story. If that doesn't fit either, maybe you are not seeing a basic trig identity that you can pull off. So it's like, it is 1, 2, 3. There is infinite amount of combinations of powers that you can get. But it's only 1, 2, 3 in terms of solving it. And if in any case, right, you run into the secant cubed, right? You know what the integral for secant cubed is. It took us 30 minutes to get there, but you know the answer. And you can insert that as a block inside. The last pair is what? Yes. Cosecant, cotangent pair. I can work this one out in 7 seconds. Same as secant tangent pair, but with negatives. Just add negatives. How about that? Because your derivative of cosecant, well, let's go with the cotangent first. Derivative of cotangent x is negative cosecant squared x, which gives you that the integral of cosecant squared x dx is negative cotangent x plus c. Your derivative of cosecant x is negative cosecant x cotangent x, which gives you that the integral of cosecant x cotangent x dx is equal to negative cosecant x plus c. All of the problems are identical. The only difference is that you have to shovel these minus signs. Right? So now, is cosecant, integral of cosecant cubed going to be less annoying, more annoying, the same? It's just going to be the same. Well, you have to just account for those minus signs, but it's going to be the same. Yeah, it's going to be the same. Just with you're just going to add your minus sign. So technically, you can go and rework all of the problems as the exercise that I had. You swap tangent for cotangent and secant for cosecant, and just put the minus sign, right, for the whole thing. And that ends this. We're going to take a 5-minute break. When we come back, we're going to do 8.4, which is this, every problem again. Because your trigonometric substitution is going to take your regular, x to the 3/2 divided by blah, 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 and turn it into trig. So you can use this to solve the problem. because you won't be able to do that problem in any other way. So, see you in about 300 seconds.